All right. So, all right. So there's a few concepts that you come back to over and over again in electricity, so we're not gonna you're not gonna absorb this like the first time, the second time, maybe third, fourth time, whatever. It's okay. But I did want to start with some of the big things that will be coming up over and over again that we will be using to make decisions about how big our wire is, what our system looks like, all this stuff. So actually it'd be good, does everybody have a means of taking notes? Yeah? Okay. So everybody has heard the terms watts, voltage, and amperage, right? Okay. So does anybody know what those things are?
Watts is power.
Yes, watts is your total power, right?
Volt is like the current.
Amps are the current.
Amps are
Yeah. And the volts are the potential. If you don't have volts, you don't have the potential of shocking yourself. No matter how many amps it is, if you don't have any volts, you can't hurt yourself. These are 3 volts. I can lick my fingers and put them on this. Because it's 3 volts, my skin stops it. It's only 3 volts. What's the plug? What voltage are the plugs?
120?
Yeah, 120, right? Yeah, everybody knows what happens if you touch that, right? So the point at which that becomes dangerous is around 48 volts. 48 volts is still very safe for dry skin, but that is the point at which the code, the electrical code, says that wires must not be exposed, because that's when it kind of starts to get dangerous. I wouldn't, if this was a 48 volt battery, I would not be doing this, just out of precaution. It probably still wouldn't shock me, but somewhere around 60 volts is where you start getting shocked. Okay, so here's the main thing we use in solar for as far as our math goes. Watts equals volts times amps. So that means that if I have a 1200 watt appliance and I'm running it on 120 volts, how many amps is that appliance? It's 120 watt appliance. I'm running at 120 volts. How many amps is it?
1.
There you go, 1, right? Because 1 times 120 is 120.
And the sun,
Right. Oh yeah, no, that's all. No, that's all good. That's it. Watts equals volts times amps. Another way of saying that is power equals potential times current. The volt is the potential, the amps are the current. And you can't get any work done without both of them. Another way of saying that is, I just came up with this last night actually, I'm pretty happy with it. Voltage allows the electrons to move. The current is how many electrons are moving through the wire, through the circuit. And interestingly, this doesn't have anything to do with what we're doing. Interestingly though, all the electrons move on the outside of the wire. They actually don't move on the inside of the wire. It's all of the electrons are moving on the outside of those copper or aluminum or steel or human flesh. Well, actually that's different because it gets in. Never mind. That one doesn't count. Okay. Does that start to kind of get people's minds working on that stuff? Okay. We're going to get right into this, and everything's going to help reinforce this stuff. So we're just introducing concepts right now. Okay. Electrical load. Does anybody know what an electrical load is?
Think how much the
close. That's ampacity.
What's the battery?
Huh?
With a battery?
No. So an electrical load is just the thing that you're plugging in, the thing that you're powering that's consuming electricity. That's a load. If it consumes, huh?
Draw?
Yeah, draw. Yeah. Loads draw the power. That's an electrical load. So you plug. That swamp cooler has a pump and a fan. It has two electrical loads. It has a pump and a fan. Those are each loads. DC and AC electricity. Does anybody know what those two things stand for?
Alternating current.
Direct current.
Yeah, alternating current and direct current. Actually, Dom, do you have a friggin' white board
Yeah.
marker? I'm gonna grab the board. Just to demonstrate really quickly. Does anybody know what the difference is? Did anybody see that Tesla movie? Not the bad Tesla, the good Tesla. Sorry, I'm. This is the first time I've done this workshop, so y'all are helping me develop it, and I appreciate your patience throughout this process.
Do you want to put it on a chair?
Yeah. Oh, that'd be awesome. Thank you, Amber.
We might also have an easel.
I should have told Dom. I'm flying by the seat of my overalls. Like, yeah, that's great. We're not going to use this very much. I just want to show what happens.
It might be too big.
Oh my gosh, that's such a good idea. I'll just do a Sharpie. No, I'm kidding. Okay, so since I slacked, I'm just gonna say, okay, so direct current is a constant voltage. Okay, direct current, something that is 12 volts on a direct current circuit. Other factors factors out of mind. Thank you, sir.
Yeah.
Direct current is a constant voltage. So if you look at a chart, so we got, this is 0 volts, and this is, it doesn't matter, time. I did that backwards, because I'm not a mathematician. This axis is volts, this is time, all right? So if we've got a 12 volt direct current, it stays the same the whole time. You know, unless it's affected by something else. Okay. This is direct current, DC. AC, alternating current. Does anybody know what happens to, can everybody see this lower one? Sorry. Yeah? Okay. Does anybody know what happens to this line?
It's a sine wave?
Yes, exactly. It's a sine wave, squiggly. The fun synthesizer thing. Okay? So this is 12, say it's a 12 volt AC. It's really rare, but that's just what we're going to go with. And this is negative 12 volts. Okay? Hertz, 60 hertz, 30, that which means 30 times a second, the voltage becomes 0. So it's only at the peaks of that 120. It's only at the peaks every like microsecond or whatever, like, so this is 1 second. Or sorry, that's not true. It's not 1 second. But this is 1 cycle. So alternating current goes up, comes down to negative, goes up. Okay, so it's the electrons are literally going back and forth 30 times a second. And that's if you have an audio system that has a ground fault and you get a buzz, that's 60 hertz. That's 60 hertz. It's actually a B on a keyboard. That's a little fun. Anyway, so that's DC and AC introduction. And then we have one more thing here. And I'll bring up We'll just use this one. Okay, because I'm really hard on equipment and AA battery cells. About 3 volts each, right? Do you know why they're flipped like this? Anybody? 'Cause I'm not really expecting anybody to know that. The reason they're flipped like this is because the positive is connected to the negative, and the negative is connected to the positive. Okay? That's called a series connection. Negative to positive and positive to negative connections. Okay? This, which means if these are 3 volts each, I think they're less than that actually, but if they're 3 volts each, this is a 6 volt device. You add with series connections, plus to minus, minus to plus, you add the voltage together, and the amperage stays the same.
Is this similar to a car battery?
In what sense?
I was just thinking about the positive and negative.
Yeah, well, so a battery is made up of cells. Hi.
Grab some more chips for us.
Oh my gosh.
So a battery in a car is 12 volts, right? Typically. Your typical car, that was weird, I've never done that before. A little nervous, I guess.
We do another table in the
Yeah, sorry.
Sorry, guys.
No. Thank you. Hey, Sydney. It's good to see you. This is great. Thanks everybody for coming, by the way.
Yeah.
I'm a happy clam right now. This is great. Everybody settled? Y'all want to just introduce yourselves, say why you're here?
I'm Austin. We live off-grid, and we are always looking for more information on off-grid stuff.
This is Avery.
This is Margaret.
She's lived her whole life off grid.
Yeah!
I'm in a yurt.
Yep.
Heck yeah, you're ahead of the curve.
I'm Sydney. I live off grid. Friends. Yeah.
Yes. Okay, so positive to negative is a series connection, and you add the voltage, the amperage stays the same. Parallel is the other kind of connection. If these were facing the same way in this device, it would be a 3 volt device. And the positive of the batteries would be connected to the same terminal on the batteries, and the negative would be connected to the negative. Yes?
You said that the amps stay the same on the...
On series connections, yes. Yep. And on parallel connections, you connect all the plus to all the minus, right? And in that case, it's the opposite of series. The voltage stays the same, and the amperage gets added together. Okay? So, now we're gonna get into our intro game with these here cells right after I read this thing. Electrical theory will be embedded throughout the course. We'll have question and answer section on electrical theory in each workshop. But yeah, I think it's just better to demonstrate most of these concepts practically. That's how I learned them. I was a solar installer for 10 years. I was licensed residential electrical contractor in New Mexico and Seattle. I built 2 of these off-grid generators, one of which was stolen, the other of which is out on the Navajo reservation. Anyway, so consider having a separate page in your notebook just for theory stuff and its applications. I don't know if that's actually going to be useful, but it was a consideration. It's like an idea I had, like it might be a good thing. Okay, so here's our intro game. We got to split into 3 groups. So 1, 2, 3. Cool. 12 people, I think. Cool. So I have 3. Anybody know what these are called? Huh? What? Yeah, electricity meter, multimeter. It's a multimeter because it measures more than one thing. That's why I call it multimeter. It measures voltage. This one only does voltage and amps. These 2 do amps and voltage. And each one has a dial, except for this one, it has a little switch. This is the one I carried with me in my little chest pouch on set. And they say one of them has a V with a squiggly over it. Is that AC or DC? Yep, that's right. And the V with the line and the dashes over it is the other one, right? The A's are your amperage, and the way you measure amperage, you can't measure amperage with probes like this. You have to do it with a clamp. These are called clamp meters as well.
Is that because of the movement around the wire?
Yeah, so what's in here is some kind of magnet,
Yeah.
and it measures it by induction. And this is like way forward. You don't have to write this down. But induction is the electromagnetic field that electricity creates as it moves through things. And that's how these work. It measures, you clamp it around a wire, and it says, okay, I can tell the magnetic field is this strong, so there's this many amps running through these wires. So that's really all we need on this for now. What about just the little ohm symbol, just to be complete about it? Does anybody know what that signifies? Yeah, resistance. Yep, resistance, and that's the voltage. Resistance stands for kind of like the voltage it takes to complete a circuit. Okay, so everybody stand up and get in your numbered groups. Everybody's going to get a meter. Please turn them to... Oh, yeah, sorry. Splitting up the parents. Okay, we'll figure it out. Oh, yeah. Okay, cool. All right, here's, you guys can have this one. This one, no, that one's less good for this exercise. This one, okay, everybody just take a look at the things real quick. Take a look at the little symbols, and then we want to turn those on to DC voltage. I don't know how to do it. Okay, we'll just go with this. It'll be okay. We can. Okay, so I'm bringing cells around, and everybody's going to kind of commandeer it. And then, so what we're going to do is these cells are in different states of charge. Okay. We need to figure out which, we have to put 4 together. So they're 3-volt cells. They're lithium iron phosphate batteries. Don't have to write that down yet. We can get to that later. Lithium iron phosphate battery cells. And they're nominal which means their nameplate voltage is 3.2. Okay. Now, yeah, they're in different charge states and just different states of repair, because I got these from a buddy of mine for free, and so everybody, let's have. Actually, let me just read this because I'm tripping up. So there are the cells in 3 different charge states. Blah blah blah. Oh yeah, I would suggest taking notes as we're making our readings, and if we could look closely at the top of the battery cell. On each end of the battery cell, on the lip right here, there's a plus and a minus. And you can see where the plus and the minus is. You can barely see it, but it's there. I promise. Okay. So you take which probe on your multimeter do you put on which terminal? Black on negative, red on positive, right? Does anybody know what happens if you accidentally, just in a testing circumstance, okay? Just in our diagnostic, just using these things, what happens if we accidentally get that wrong and go the other way around? Does anybody know?
Zero, right?
The electricity goes the wrong way.
Yeah, so exactly. So that means actually that you will get a negative reading. And that's part of how you can tell eventually if stuff's wired backwards. You can be like, oh shit, this is negative. I'm putting the red to the positive and the black to the negative, and it's reading negative. There must be some reversal going on. Okay, and that's only in a DC circuit. In an AC circuit, it doesn't matter which probe you put to which. Why is that? Anybody know?
Oscillates.
It oscillates, exactly. There's no way your probe's gonna know it's changing 30 times a second, and it's constantly changing. There's no way. So, and the electrons are literally going back and forth. So there's no way that you could actually get a reading. So it kind of takes, it's called an RMS. It takes a root mean square average of that, and that's how the AC voltage gets out. Okay. Actually, that's not true. It takes the peaks, not the RMS. It takes the peaks of the voltage. So, you gotta remember to correct myself. Bullshit. Okay, everyone has a number. Every battery has a number. So let's measure the voltage on the cells in front of you, and just like write down what the voltage is for each number of cell.
How much did this cost?
That one's like, I think those ones are like probably like $60. You can get, for these purposes, just get a cheap ass one off of freaking Amazon or whatever,
Yeah, a
Harbor
little
Freight.
brick $15 one will be okay?
Yeah, although you do need, if you're gonna make your own battery, you want an amp plant. If you're not gonna make your own battery, you don't need it, but it's a nice one once you get the panels in. Because you can put it around the panel wire and see, okay, I'm missing a panel because I'm this many amps short. I know exactly 1 amp's worth of panels short.
So when they say amp hours, what does that entail?
We're gonna get to that.
Okay.
We're gonna get to that. Amp hours, yes, that has to do with capacity. Oh. Gotcha.
Harry, who are all these people? Luckily, we had
That's the wrong one. Is everybody done? Almost. Sorry. Yeah, we had the cap debacle. Sorry. Okay. Which one? Everybody, all at once. Which one is the lowest voltage? 5, right? What did we get for 5?
0.3.
0.3.
I got stuff.
I got these cells from my friends.
0.3.
They're 5 years old. They sat around for literally 5 years. This one's dead. This one's just garbage.
No way to bring it back.
There's no way to bring it back.
Okay.
If it goes down that low, if it goes down much below 2.5 volts, it's going to damage the cell. Although these are extremely robust. If you left the car battery around for 5 years, or an AGM, or any other kind of non-lithium battery just sitting around 5 years, none of these would be good if it wasn't lithium iron phosphate.
So is lithium polymer and lithium phosphate the leading in the industry right now?
Yeah, lithium iron phosphate are the leading deep cycle, meaning they're meant to be discharged very low to low percentage. They're the leading deep cycle battery in solar. That's what Tesla Powerwalls are made out of. That's what all the big battery brands are made out of. Okay.
They ain't cheap.
They ain't cheap.
They ain't cheap.
They're also
That's not bad. This is charge. Okay. So this is 100% charge, and this is 0% charge. All right. The voltage charge, the voltage to charge state, right? It's just like your phone, the little battery friggin' thing. That's your charge state. 100% is fully charged. 0% is not. That's your charge state. And the reason that I wanted to do this battery building exercise is A, it's way cheaper to build your own batteries, and B, if you can understand the underlying components of everything. I think if I would have learned shit this way, stuff this way, I would have learned it a lot faster. But I got piecemeal on the job, like whatever. But if I understood the components and understood how they all work together and all of that, I think I would have learned it a lot faster. So that's why we're doing it this way, in case anybody was wondering. Okay, so 3.3. We're going to skip to 3.4. Okay, so 100% is 3.65. That's the absolute maximum that we ever want these cells to be charged to, 3.65 volts. And then, at about 90%, it goes down to 3.4. Like super soon. Right there. Okay? Then past 90%, a little bit past 90%, it goes right down to 3.3. And then it stays there. It stays at 3.3 volts for most of its charge cycle. Between about 20% charge and 90% charge, a little less than 90% charge, it's going to read 3.3 volts. And this is important because this is so not to scale. But the reason this is important is because when it's in here, between about 85 and 25%, we have no idea how well these cells are charged. Because if it's 80% charged, it's going to read 3.3. If it's 30% charged, it's going to read 3.3. We have no idea the state of charge of these things. So what did we get for some of these other ones? What are the 3 highest ones?
We got 3.4 on, I think, number 2.
2?
Number 2.
Okay. Did any other ones read 3.4?
One had 3.4.
On which? Number 1? Okay. 1 and 2 are 3.4. What's our next highest one?
3.3.
3.3. And which one? All the rest of them, right? Okay. Except number 5. Okay. So that's actually get this one. Let's measure these two. Sorry, we'll do this real fast. This one's going to be 3.34. This one's 3.28. Okay. So 3.34 is number 3. That's pretty high. What were 7 and 6?
7 is 3.3.
Okay. Did anybody get the second digit for these two?
Yeah, 3.30
Uh-huh.
for 7, 3.31 for 6.
Okay. So we want this one. Okay. This is a little higher. And then 3 point. I'm sorry. Which is the next highest one after 3, 2, and 1?
3.31 for 6.
Okay. All right. We'll call that good. This is probably the ones that I charge almost all the way. But that's the squirrely thing about this stuff is that sometimes they do things that we don't necessarily expect them to do. Okay. So let's everybody come back over here. Actually, maybe we can crowd around the middle real quick. Someone wants to have me put these cells on. Okay. We're gonna face them all the same way. Do we remember what the term is for connecting positive to positive and negative to negative?
Parallel.
Right, that's parallel. Okay, so presumably these are somewhat close to our highest charged cells. These are bus bars. Okay? Bus bars. BUS. When you bus, just like a city bus. When you bus things together, you're connecting like to like. That's what it means to bus something together. So we have to, because we know this, right? Because these 3.3 ones, we don't know where they're at in this charge cycle, okay? We have to balance these out so they're all the same state of charge before we hook them all together. Okay, so the way that we do that is, can we, is it possible to gather it's probably not possible to gather everybody in the middle here, is it?
I think we can do it. Yeah.
Let's try it, let's just try. So,
Yeah, because we're gonna put those all together.
so we're gonna put these all together in parallel. And what do we add up when we put things in parallel? Correct.
Say that again?
The amps.
Yes.
When we put things in parallel, we add the amps together. So, somebody take 3 of these. And these are aluminum. The reason I trust these better than these is because these are steel coated with some kind of thing that helps it conduct electricity better. These are completely aluminum. We will not be using these in the eventual installation, but we're going to use them for this purpose.
You don't ever find those in copper?
You can. You could even, honestly, if you got some scrap copper tubing and you pounded that some gun flat, you cut it, pounded it flat, you could totally use those to make buses. Absolutely. Absolutely. I like the way you think. Okay, so we're going to kind of do a little hat thing so we keep all our things together here. Now, yep, good. Good. Now, here we have, we were going to build these, but we're already an hour in and we have a lot of stuff to cover. So, this is a buck converter. It changes DC voltage. So, this is an 18 volt power supply. This is just off of a radio. This is just a, This is a buck converter. Buck, yeah, like a doe or a buck. It takes one DC and outputs a different DC voltage. So, what you can do if you end up doing this is you can use any 12 volt or or just about any DC power supply with these buck converters. Where is it? Sorry. And that. Whatever. I'll just do this one as an example, kind of. Or wait, where'd the other one go? Didn't the other one have one? Oh yeah, here we go. These are called Phoenix connectors. These little greeny things. You can make yourself a little barrel connector. You can get them cheap ass off Amazon or whatever. Super useful for doing stuff like this. Yeah, it's got a plus and a minus, and then you can plug in any friggin' power supply to your buck converter.
So like if I have old laptop chargers, I
Yep.
can like use those too.
Absolutely. Or you can cut them off and run them directly into the terminals, or you can put ring terminals. These are ring terminals on here, nice and sturdy. Okay. But and it's got two little screws. One of them adjusts the voltage, and one of them adjusts the amperage. Okay. So in order to balance these, well, actually, let's get most of our screws in first. Does anybody want to do the other side here? All but one of them. And then I don't know what the hell happened to the other. Okay.
Do you think this board would be safe out in the environment, like in the weather?
We're only using these to charge and balance ourselves initially. You can make them more robust. You see these heat sinks?
Yeah.
Oh yeah, here we go.
Yeah, those kind of help cool it off because in case it gets
Yeah.
too hot.
And if you end up mounting your solar on a friggin' aluminum rail, you can cut off a piece of that aluminum rail and screw it to these things, and you can crank these things like crazy because it dissipates more heat. These things create heat as they convert.
Oh, okay. So the heat's gonna get displaced from that.
And I've done that before. You can get aluminum solar rails and friggin' screw them to these things, and you can just, I've gotten like 15 amps through these things before, and it was just fine because there was that much surface area cooling it down. And we'll talk in a minute about where that heat comes from. Okay, so then we're going to, which sides are negative? That sides are negative, so we're going to do our black one there. Yeah. We're not going to do any, and it doesn't matter where on this you do this. Supposedly. Okay? Nah. That's okay. It's fine. Everything's okay.
It's just three. It's just three. Oh yeah.
So is this
Yep.
charging?
Oh, this is 3 volts because we're in. Remember, we're in.
Oh yeah, it has.
So this is gonna be charging. I hope I didn't just burn this thing out. Woo! Spicy. Maybe we did burn it out. It is very warm. Why are you so warm? That's weird. Plus. That's very weird. I should not be doing that. Okay, let's undo that. Sometimes electrical stuff does stuff you don't want it to do. Why did it do that? Yeah, feel these. Careful though.
Yeah. Oh yeah. That's what you don't. That's what you don't want to feel.
That's what you do not want.
That is an electrical fire.
Yep, exactly. And that happens because there's too much resistance. So what is going on with that? Okay. Let's try, do we really want to burn out another one? Yeah, we do. Hell yeah, we do.
Spoken like an electrician.
Actually, let's do this first. We got to set our balancing voltage anyway. So let's do it. Before we burn this one out, let's take a look at how we adjust it. So these things, if you're going to do stuff like this, these things are awesome. Get some cheap ass alligator clippy dealies. And then you grab, could someone grab one of the 2 multimeters that has the multiple? Yeah, not that one. I'm sorry, multiple decimal points. Okay, here we go. So these are super useful. You can clip them to this. Oops, wrong one. We're gonna go yellow to negative. Clip it to that. Clip to that. And then this is the output side, right? Ooh, we don't want that shorted together. That would be not that great. Don't
stick one under the
don't do that.
yeah.
That'll be alright. Okay. So
happened last time.
I don't know. Actually, I don't know what the heck happened. Honestly, it shouldn't have done that. And it might just be the circuitry in these. I've used these before to do this exact thing, but I guess I should have tried it again. So, this is off. Now, we're going to plug this into our 12 volt power supply, because this is the one that's configured for the 12 volt. This is just a power supply off like a computer monitor or some shit. I don't know. Plug it in here. Boom. We get a light. Yay. We get a light. Why is it overflowing?
Well,
Just restart it. It'll be fine. There you go. 3.6 volts. We want to top balance these to 3.65 volts, really. So, because that's like the outside, and that'll make sure that they're all the exact same voltage. Who wants to give this a try? So the voltage control is this little guy right here. You can see there's a screw. And who wants to try and just very slowly as you can, turn this sum gun up until we get to 3.65. Nope. Yeah, see, it's like,
that's super sensitive.
yeah, it's gonna be, because these things go all the way up to 60 volts, so it's really hard to get the,
There we go. Man, if that thing rattles, it'll adjust it.
yeah, it might change a little bit. Yeah, maybe we'll try for 3.65. Yeah, there. Boom. Okay, take the screwdriver off. 3.65. Good enough for Chrysler. Okay. So, I guess we're gonna try this again. Let's unplug this. Okay. I'm really not sure why it was doing that. It could be something in the circuitry with this. We may have to use my oldie moldy one. This is the one that I have used before. It's way jankier than this one. You can see it's got smaller fins on it. This one can dissipate more power.
Can I see this?
Certainly. Oh yeah, I unplugged it. I'm like, why did it change? Okay, so yeah, let's try this. We'll see if we burn this one out. Let's try doing the, let's see, which one did we do first last time? We did the negative first last time. Let's do the positive first this time. These things are like $10 each. It's nothing crazy. Yeah, it's good. Positive first. Okay, so then someone wants to grab this little feller and just give him I'll do this first one so you can feel how tight to do it about. These all have, your batteries will have, oh great, they're different sizes. They're different sizes. What the heck?
A Phillips, right?
We can totally, I'd prefer not to, but we will.
Yeah, they'll strip them out.
We'll use a Phillip. And this is a Japanese Industrial Standard screwdriver, so it fits better. Those are very useful to have. Okay. Yeah, you have to hold them. Okay, who wants to tighten these? That's about how tight we want it. If whoever does it wants to feel that.
Looks tight, but not super tight.
Yeah, it's not like crazy. So we'll go through and tighten all these. Oh, that's one of the Phillips ones. That's so dumb. We'll change these out when we actually make the battery. That's a Phillips one. I'm sorry. I'm talking myself. Good.
Someone else?
Everybody's like, oh, I don't know, man.
It's gonna explode.
I have rest.
Oh yeah, that one's one of these. Did I get it? I think I got it. Yep, and then we can hold this. Hold our terminal so it doesn't spin you every which way. Yep, good. That's good. And then that one, same thing. I guess I should have checked the terminal screws. Okay, now, since this thing's not broken now, it's only reading 3.33 right here right now. That's very strange, but that's okay. Let's see how much power. Somebody grab the yellow one, please, the Fluke.
What were you expecting it to say?
Here, I would expect it to stay at 3.6.
Okay.
And here's the weird thing. Is usually when you're charging these, you'll read whatever your battery is here, and then whatever you set this thing to here until the battery's charged. Okay, so we're going to set this to DC amps, right? We're putting DC amps into these batteries. Okay, now check this out. We're only putting in 0.6 amps right now, which means we need to turn this thing up again. Okay, I'm gonna do this because
You want me to hold this on the?
just because. It's all right. We can read it. We've still got it attached.
Okay.
That's why these things are so great, because you can readjust. And we're gonna crank it up. So we read about, what did I say, 0.6 amps? Okay, and that's because this thing's voltage went down, maybe it got bumped, maybe whatever. So we're gonna just slowly crank this up. And it's staying the same, which is really weird. But that's what electricity does to us sometimes. It doesn't always do exactly what we think it's going to do. I didn't plug it in. I didn't plug it into the power supply.
I was wondering. I was like, so
That's like step one, right? Is it on? Is it plugged in? Which is great. It's easy.
All right. Okay. So now I need to turn this back down. That should be step one. Turn this back down so we don't blow our batteries up, our cells up. Oh my gosh, what a nerd! See, it doesn't matter how long you do this stuff. You can do still. Okay, now we're at 3.37. So now, if you watch this, hopefully this time it'll go up.
we're taking this AC and charging DC batteries through the buck.
There. Yep.
Yeah.
There, we're up to 3.4. What are we trying for?
3.6.
Yeah, 3.65.
Oh, 3.65.
We're gonna go 3.64. That's fine. That's probably within the, what do you call it? The margin of error on this thing anyway. Now, amps. Ha! Now we're pushing 4 amps into this thing. Okay? So, once we're barely pushing any amps into it, that means it's full and it's balanced out. They're completely the same state of charge.
So then it'll go down to zero.
Huh?
Is that what you're saying? The readout on the.
Yeah, it'll
It'll
approach
go to
zero.
zero.
It probably won't ever go completely to zero. And then the other way you can test it is if you check this out. Let's grab the last one, the last multimeter.
It was 4 amps you said that it's
Okay.
pushing now?
Yep. Yeah, it's doing 4 amps. Actually, it's doing 6 amps.
6 amps.
So you're just touching this to the.
Let's just go around.
Oh, goes around.
Yep, it
Okay.
reads it through in the electromagnetic field that's created in the electricity in the wire. Who's got? Okay, turn that to DC volts. It might have turned itself off.
The DSL noise.
Oh man, that's a throwback. Cool. And then this is positive. This is minus. Test our voltage at these things and tell us what it is.
It says 3.38.
3.38. It's weird, right? We got 3.65 on one end of this wire and 3.38 on this end of the wire. I don't understand. I honestly don't understand why it is like that. I don't understand how that works. But that's how it works.
Those volts? that you
Yeah, those are
measured,
volts. Yeah.
They get lost.
And the other way you can tell this is done is when this voltage somewhat matches this voltage, because then you're not pushing anyone. You're that tells you that your battery voltage is that.
So once the voltage is the same on the
Yes.
meter and
And
at
here,
that point,
that means they're
it's
all the
charged.
same and they're balanced out.
So it's on either side of the converter,
Yep.
the AC side and the DC side.
Well, okay. So in this setup, this is the AC to DC. This is like a laptop thing. All of your appliances, all of your electronics, they're all DC electricity.
Yeah.
And that's why we have these things. This converts.
That's the component.
It's called a
That's the
rectifier.
yeah.
If you want to,
Oh, it's rectified.
it's called a rectifier. You get rid of the squigglies, and you just end up with not squigglies. It's
Okay,
called a
so
rectifier.
Coming into here is AC. Coming
Yes.
out of here is DC.
Yep.
12 volts.
Yeah. AC, DC, 12 volts, and then this takes it down
Yeah.
to our 3.65 or whatever.
Okay, so 12 volts is
a
coming in, and
buck step down.
3.65 is stepping it.
Yep.
Stepping it.
Those will be built into some of those, right? Sometimes.
Yes, absolutely. Yeah. Sometimes these things, like a computer power supply, puts out 5 volts, 12 volts, and 3 volts or some shit.
You remember the Xbox 360
Um,
brick, dude, that came with?
Oh
it?
yeah, that thing was massive. Those things got
heat up
hot.
so-
They got hot
so
as hell.
And that was a step. That was a step down.
Yeah, it would basically do what we're doing here before it gets
Okay.
to the device.
So, don't worry if these are the things. Oh yeah, I didn't read that, but don't worry if there are things that we don't understand now. We're gonna get to them later. Okay, we got the balancing. Okay, so the reason that we set these like this is so that hopefully by the end the workshop's over, time the workshop's over, they will be done. Okay. So yeah, that's pretty much that's it for the intro section. I know there are questions. Are there any particularly burning questions?
Yeah,
on
just one real
this?
quick from me, which is, can you quickly explain the difference between a battery and a cell?
Yes, a battery is a collection of cells.
Okay.
A battery is these things hooked up in such a way that they are useful and create an end user situation where you can hook it up to a solar system or whatever. Right now, these are just cells charging.
Okay.
And I'm sorry, the reason that there are 4 of these, that we chose 4, can anybody guess?
Quick math. Easy
12.
math.
12.
12 volts, so it's 3 volts times 4 is 12.
Yep. We're going to hook these up in series at the end, and then it will become a 12 volt battery out of 3 volt cells.
Okay.
Thank you for asking that question.
Okay.
You reminded me of a very important thing that I forgot to mention. Yeah, that's why we're doing 4. I have 8 of these cells. 2 of them are dead, and I wanted to do a 24 volt system, but 2 of them were dead, so we're doing a 12 volt system, which is a major pain in the ass. Anytime you can do a 48 volt battery, you want to do a 48 volt battery, because on the 12 volt system, all the wires have to be bigger. Everything has to be bigger, and it seems counterintuitive, but the shit is more expensive. because all the wires
So you
have to
need
be
like a
low.
10 gauge or 14
We
gauge
don't
or
need more than that.
8 gauge?
What?
And this is number 2. We're gonna get to this. Don't worry. We're gonna get to this. Okay. So we're connected in parallel. We're balancing the batteries. This is called top balancing because we're charging them to the top. You can bottom balance too, which means you discharge them all the way, and that equals out the voltage. But that's only if you're planning on discharging your batteries really low a lot, such as for an electric bike or I don't know, whatever else. Doesn't matter. We're gonna top. I've always top balanced. Okay, we connected into the power source. We chose our voltage because we want to get everything up to 100%. We talked about the charge curve, right? We'll come back to that at the end. We checked our amperage flowing in. We checked the voltage of our system. Cool. Okay. We got through the intro. Now on to safety. Do people want a quick break?
Yeah.
Yeah? We want to take like a 5-minute